That's Brooks's theorem. It's difficult to prove. It's beyond the scope of this course to prove that. So we're going to prove a sort of simpler version of it. Okay, so this theorem implies that a simpler result, which in the notes is called a proposition, it's almost the same statement, but instead of talking about specific graphs, which you have to remember, all I'm telling you is that the graph is not regular. Okay, so if we have a graph that's not regular, that means not all the vertices have the same degree. It still has to be connected, then we have the same conclusion. Now this is a much weaker statement because these two graphs, these nasty graphs, they are regular. Their vertex degrees are all the same. So of course, the key point here is that both Kn and the odds, and any cycle, in particular the odd ones, these are regular graphs. The vertex degrees are all equal to delta. So because of that, we can certainly, if Brooks's theorem is true, this proposition is certainly true, because by saying not regular, we're ruling out, in particular, the nasty examples. Unfortunately, we're ruling out lots of other examples, because there will be lots of regular graphs which can be coloured in this way, but at least this proposition is something I can prove without too much pain, and I'll do that today. So I want to effectively prove this proposition by giving you an algorithm that colours the graph in at most delta colours. Okay, so given a graph, we work out the maximum degree, and we can colour it using at most delta colours. That's what I want to show you. And the way this is done is by a two-part algorithm which I'm now going to explain with an example. It's the same example as in the notes. So this, in order to prove this proposition, we're going to do it constructively. We're going to find a colouring with at most delta colours. And the first thing we do is we have to take a specific order of the vertices. We have to be careful how we order the vertices. And we're going to order them with what's called a breadth-first search. And this will be an important concept for the course, but I'll explain it for this example. What it means is basically you start with a vertex and you look at all the adjacent vertices and you add them up, you add them to a queue and you keep going. So the idea of a breadth-first search as opposed to a depth-first search is we use a queue. That's the key sort of concept. Once we've ordered the vertices, so we've numbered the vertices in some specific order, we then do an obvious process to colour the vertices. We use what's called the greedy algorithm, which just means you colour them in the order in which you're given them, without really thinking. I'm going to explain these two things with the example of the almost dodecahedron graph from the notes. Let me just leave that for a minute if you're taking notes. Now this two-part algorithm is sometimes called Brooks. The two things together is sometimes called Brooks's algorithm. I don't like doing that. I just prefer to call it the two-part algorithm. That's the two processes put together. And the other key factor is that when you've ordered the vertices, you actually have to take the order backwards. That's important. I don't like calling it Brooks's algorithm because it doesn't prove Brooks's theorem. Brooks's theorem is much stronger. This is only proving the theorem under the stronger hypothesis that the graph is not regular. So it's two-part algorithm. First of all, you order the vertices, you put them in a queue that gives them an order from the first to the last, and then you just colour them in reverse order. So let me explain that using this graph which you've seen before. Now I've got to prove the proposition, which means I want to start with a non-regular graph. I'm not doing anything for regular graphs. The graph I start with has to be not regular. So that's why I've removed this edge. You see, this is the dodecahedron, but I've removed an edge. There's no edge from 1 to 6. I've done that on purpose so the graph is not regular. So this graph is essentially the dodecahedral graph. It's the edges and vertices of a dodecahedron with pentagonal faces. Minus one edge. With this numbering, it's minus the edge I've removed is the one joining 1 to 6. So it's not regular because I've removed this edge. This has vertex degree 2. This has vertex degree 2. All the other vertex degrees are 3. So it's not regular. Now there's another thing which I didn't say, but I wrote it out here. You have to start from a vertex whose degree is not maximal. That's where I'm using the fact that it's not a regular graph. We want to prove this for a graph that's not regular, so there will be some vertex whose degree is not delta, it's less than delta. So that's where we start. So that's crucial. So we've got two choices. We've got two vertices that don't have maximum degree, 1 or 6. And following what I did in the notes, I'm being perverse. I actually start from 6 rather than 1. It doesn't matter. I'm going to start from 6. So I'm going to start here. This has degree 2. We're going to start with vertex number 6. So start from vertex number 6, which has degree 2, which is less than delta, which is 3 in this case. The maximum degree is obviously 3. Now what it told me to do was to order the vertices, or reorder them. They've already been ordered here, because I've ordered by the pentagons, 1, 2, 3 on the inner pentagon, and then where there's 6, then I don't know how I've ordered the rest. But they've already been ordered, but that's irrelevant. The order that was given, I don't know quite how they were ordered, but that order, the numbers are irrelevant. We've got to reorder them. And we're going to start from 6. So what you do is you form what's called a queue. And I'm going to, first of all, I'm going to do this in shorthand because I don't have much space here, and then I'll sort of explain the concept without the diagram. So we're going to start at the top of the graph, so I can remove the bottom for the moment. We're going to start with 6. So we put down 6. That's the first vertex. And then we do this idea of a breadth first search. That means you look at adjacent vertices. So you start from 6 and you look at adjacent vertices. And there are 2 adjacent vertices to 6, 11 and 15. And you have to put them down after 6. And you can put them in either order. But to be definite, if we were a computer, we need an instruction. Which one do we put first? And since they have been ordered in this case, we may as well put the smallest one first. Or you could put the biggest one first, but you need a rule. So let's put the smallest one first. So after 6 we put 11, and then we put 15. Then on the graph, it's very important to cross these vertices out, because you don't want to put them in the queue twice. So we've done 6, we've done 11, we've put 11, and we put 15 in the queue. And stuff goes on the queue from the right-hand side. Okay, then what we do is, in a sense, 6 comes off the queue, or I'm going to just tick it to say it's been dealt with. So now we go to the next one in the queue, after 6, which is 11. because this is the front of the queue, if you like. This is the front of the queue. You know, this is sometimes called the first in, first out principle, because 6 gone, 6 has gone in first and it comes out first. It's the idea of the queue. Okay, so we've done 6. The next vertex to sort of position ourselves at is 11. And we look at all the vertices adjacent from 11. But we never go back to one we've already seen. So 6 has been done, it's been crossed out, so we forget that. And there are 2 other ones adjacent to 11, namely 7 and 16. So they go in the queue in that order because I'm putting the smallest one first. 7 and 16. And I must remember to cross them out on the graph or on my table if I have a table. Going to need more space. So I've now dealt with 11. In a sense, that's sort of come off the queue, so I don't have to do anything anymore. And then I go to 15. I go to the next one in the queue, coming about at the front of the queue is 15 now. So I now position myself at 15 and scan vertices adjacent to 15, forgetting about 6. So I have 10 and 20. So they go in the queue in that order. And that's dealt with 15, but I must remember to cross out 10 and 20. And then I've come to 7. So, well, I shouldn't have ticked it until I've written down what's adjacent to it. 7's adjacent to 2 and 12 haven't yet been done. So that finishes 7 off. Then we go to 16. We don't go to 8. We go to the next one in this queue, which is 16. Where's 16 gone? Right at the top. So 16's in the queue. I put it in the queue. The cross means it's in the queue. We can still position ourselves there. And that's adjacent to 17. Well, 20's been done, 11's been done, so the only one we have to put in the queue is 17. Okay, is it clear what I'm doing? I don't need to go on. You want me to do one more? Thing is, I've lost where I was now. So 17, so we put 17 on. That was scanned from 16, but now I've now done 16. So I now look at the next one in the queue, which is number 10. Number 10 is adjacent to 5 and 14. So they get shoved on. 15 was already there at the beginning. And that's done 10. And now I come to 20. 20 is adjacent to 19. The only one that hasn't been done is 19. That does 20. Then we come to 2. 2, the only thing to put on is the 3, is the 1. Sorry, the 2 is adjacent to... Where is 2? 2 is adjacent to 1 and 3. I haven't crossed either 1, has to be crossed out now, and 3. So it's 1, 3. I may as well go to the end at this point. Can you still see? Yes. So that does 2. Now I'm come to 12. 12 is... hard for me to see. 12 is there. The only thing I have to add on is 8. I may as well use the black pen. That does 12. 17 is, I have to put an 18, and 18 is, you can't see, 18 is adjacent to 12, hasn't been ticked off. So 18, that does 12, 17 rather. Then we're on to 5. 5 is adjacent to 4, it's the only one missing. 14 is adjacent to 9, and 14 is adjacent to 9. What happened to 19? 19 was already there, but I forgot to cross it out. Someone didn't remind me to cross it out. 19 got added on, so it should have been crossed out. So 14 is adjacent to 9. I'm almost finished now. So 9 gets crossed out. We've only got one vertex left. We go to 19. Everything's been crossed out, so that nothing to be done there. And then we go to 1. 1 is been done. 3. Anything new adjacent to 3? How do we get the 13? Maybe from the 8. Yeah, 8 is adjacent to 13. So we can stop there once we've got all the vertices. We can cross the 13 down. So that's my reordering of the 20 vertices. I've reordered them, and this Q has a particular property, which I'll explain. Okay, so we've produced this reordering. That's the first part of the algorithm. Now, having produced that reordering, I'm now going to colour the vertices in reverse order. And now colour the graph using what's called the greedy algorithm, which I'll explain, but it's an obvious thing, in reverse order. Now, in a moment I'm going to have to remove the Q. What does that mean? It means I start at the last vertex I got to, which was 13. And we can go start near the bottom, we can remove the top bit for the moment. So I start with 13, and that becomes the first colour, alpha. Then I go to the next vertex. I don't go to the adjacent vertices to alpha. I go to the penultimate vertex, and so I'm going backwards now on this Q. And so the next one is 9. Well, that happens to be adjacent. I can't use alpha, so I use the lowest colour possible. So colour the graph in reverse order, always using, this is really the greediness, always using the lowest colour possible. In this case, it means alphabetic. I'm using my Greek letters, remember, for colours. So we've done 9, now we do 4. Now 4 is adjacent to 9, but it's not adjacent to 13, so I can use alpha for 4. I can colour 4 with alpha. You have to correct me if I make a mistake. So then I go to 18, so I'm using this list. So 18, that's off the bottom, that can be beta. Because it's not, it has to be beta. And then we do 8. So 8 can be beta. Quite quick, this is very, very quick. 3 has to be gamma, because 3 is adjacent to it. I'm going backwards on my list. 3 is adjacent to both an alpha and a beta. So it has to be gamma. And then 1 can be alpha. See, 1 is not adjacent to anything, so 1 can be alpha. 19 is also an alpha. 19 is adjacent to beta, so it has to be the lowest colour, which is alpha, not gamma. 14 has to be gamma. 5 can be beta. Well, it can't be alpha, so next colour is beta. It can be beta. 17 is, there's a beta there, so it can be alpha. 12 has to be gamma. 2, alpha gamma can be beta. The question is, will I need a delta? 20 has to be beta because of the alpha here. 10, we've got a beta and a gamma, so 10 can be alpha without difficulty. 16 has to be gamma, so it's adjacent to an alpha and a beta. 7 can be an alpha. 15 can be a gamma. 11, almost finished, has to be beta. And there's no problem at 6 because it's only adjacent to 2, so that can be an alpha. Now I've done this with 3 colours. Okay, so procedure, does that make sense, the procedure? You've got to remember to start from the reverse order. So you order the vertices using this Q idea, and then you start from the back of the Q to colour the graph. And the idea, what does it mean, a greedy algorithm? It turns out that this algorithm, for reasons I'll now explain, will always colour the graph, provided the graph wasn't regular and you could start with a vertex when you ordered, you could start with a vertex whose degree was not maximal. This will always colour the graph in at most delta colours. That's what the proposition says. So here the maximum was 3. Remember, delta was 3, so that's why we were able to colour the graph in 3 colours. So I knew already that I wasn't going to need a delta. It wouldn't have been obvious had I had this edge. In fact, I think with this edge it doesn't make any difference. But the proposition, it wouldn't have been obvious, even though Brooks's theorem still tells you you're okay because this is not one of the nasty graphs. This method will not necessarily achieve the colouring in 3 colours, had the thing been regular. So you can try that in this example by putting this edge back and doing the thing all over again. Anyway, in this case, we know that we only need 3 colours, and this method will give us the 3 colouring. So let me explain. I was saying, why is this idea of colouring starting at 13? Why is that a greedy algorithm? Because the idea is you don't really know the end result. The end result is that when you do all this procedure, you are actually going to colour the thing with delta colours. But the process we're doing as we start is just doing an obvious thing of taking the lowest colour and then looking at adjacent vertices and making sure things are working at the time, but there's no guarantee that at the end of the whole graph everything's going to work. So the idea of a greedy algorithm is you do what seems to be right at the time to satisfy yourself, like eating a lot of food, which means you might not have room for better food later. But if it works out, in many instances this greedy idea works out and actually gives you the best procedure that can be verified that it works and gives you the result you want. So again, I'd like to tell you why this works, and because the idea is very simple, and I think it's worth just explaining why this works. So what I'm essentially doing is I'm proving for you the proposition, because with the aid of this example I'm explaining why this method will always give you a colouring with at most delta colours. This 2-part algorithm, why it will always give you what you want. So here in our case is the Q typed out a bit more neatly. We started with vertex 6 and we ended with vertex 13. Now the important thing is the property of the vertices in this Q. The first thing is that you must make sure that each vertex occurs exactly once. Okay, and that was part of our procedure. I nearly made a mistake, but that's why I kept crossing the vertices out, to make sure I didn't put in the same vertex twice. There was nearly a problem with 19 because I'd forgotten to cross it out. So you must make sure that each vertex only goes in once. Once it's in the queue, you forget about it. It's what's called visited. So often these algorithms, as a sort of you're standing at a given vertex and you look at all the adjacent vertices, and if you've already been at a vertex, you forget it. You don't see it. You pretend it's invisible, and you sort of see the other vertices. So that's the first property. The second property is that how did we get these vertices? Apart from the first, which we started artificially, how did we get these vertices? For example, how did 7 get in the queue? Well, 7 got in the queue. I used this other diagram in which I've actually put the colours on. With gamma is... Here's a sort of representation with the colours. I think it should be the same picture in which yellow is gamma, green is beta, and red is alpha. So that was what we actually found, putting colours in rather than Greek letters. And what I was asking is, how did we get 7 in the queue? How did 7 come in the queue? Well, 7 came in the queue because it was adjacent to 11. We started from 6. Then we put 11 and 15 in, so the second one in the queue was 11, and 11 saw the 7. So the 7 came in because it was adjacent to 11. Okay, so the 7 came into this queue because it was adjacent to 11. It was seen by 11. Now, the other two adjacent vertices to 7 were 2 and 12. So adjacent to 7 were 2 and 12. That's why they got into the queue there. And this is the key point, you see. Each vertex, apart from 6, most of the vertices had degree 3, but they only got into the queue because there was a vertex they were adjacent to on the left. So each vertex in the queue is going to have at most 2 vertices adjacent to it on the right. Okay, that's the key point. So because each vertex came in the queue because it was seen from the left, that means one of its, remember, delta is the maximum degree, so we've already used up one edge to actually see the vertex. So that means that the vertices yet to go in the queue, there can't be more than delta minus 1 of them, in this case 2. So each vertex here, there will be at most 2 it's adjacent to on the right. And that's also true of 6, because we chose 6, so it didn't have maximum degree. So 6, it can only be adjacent to at most delta minus 1, in this case 2 vertices. In fact, 6 was adjacent to 11 and 15. So actually, every vertex in the queue now has this property that every vertex in the queue, I've written it here, has at most delta minus 1, I'm doing it in general, in this case delta is 3 in this example. Every vertex has at most delta minus 1 vertices to its right in the queue that come in after that vertex. That means that when we colour from the right, starting from 13, we're colouring in this direction. Whatever colours we've used for these vertices, when we come to the next one, for example, when we come to 7, we only have to worry about adjacent vertices, and there will be at most 2 adjacent vertices to 7. So whatever colours we have here, there'll always be a spare colour left over within the delta, within the set of delta colours. Here, delta is 3. So there'll always be a third colour for every vertex in this queue, because we've used at most 2 beforehand. Is that clear? So that's why this method works, because it depends on the property of this queue. That's all. That's the end of the proof. So this explains, this essentially justifies, this really proving the proposition, proving why the method works, and shows you that all the vertices can always be coloured with at most delta colours, provided the graph was not regular, because we needed to make this choice for the first vertex to make sure that there were at most delta minus 1 vertices adjacent to that.